atom, let it be r. This is just radius of the atom. I'm just showing in this particular way. So this is a light source. What it will do? It will emit a photons. This one. So the power of source, let it be 25 watt. Then the wavelength of light emitted by it, let it be 5000 Armstrongs. Then it is placed at a distance of 1 meter. And the radius of the atom, so what is r? R is radius of atom. Let it be equal to 1 Armstrong. So, and the work function of this metal, let it be, say like a 4 electron volt. I'll take it. No, after what time the photoelectron will be ejected here? Now for this, what is the method? First, we should calculate what is the intensity of light at here. How much of energy is incident at this one? So what is the intensity of light at this particular point? Power by 4 pi x square. Now first, what is the energy of photon? See, when that particular electron will become free from the atom, let's assume that when that electron will become free from the atom, when the incident photon, if it gives continuously the energy, what happens when the energy of the electron becomes greater than work function to become free from the atom. So overall, the light which is incident on this particular atom, I'm not discussing anything here, the photon concept. I'm discussing about the wave nature of light here. According to wave nature of light, the light emitted by source will continuously fall on metal. I'm just considering some like a circular area of radius 1 Armstrong. So that I'll call that radius of atom. The light is incident on it. When the light is incident on it, and we know that the light what happen will impart energy, it will be generated, and that it will be absorbed by this surface. And when that electron will come out, when the energy gained by that electron becomes equal to work function, that electron will be ejected by this circular surface of radius r. So how to calculate the energy incident on it? I'll proceed with this. I don't know anything about photon. I don't know anything about photons. So I'm taking help of the wave nature of light. What is the intensity of light incident at this point? Ps equal to 4 pi x square. Will I agree? Then energy incident on the surface of radius r. So this is what I'll call EI. This should be equal to how much? Intensity into pi r square. What is this? This is some sort of like a watt per meter square, no? So shall I introduce delta T here? Intensity is what? Power flowing per unit area. So how much of energy incident per unit time? How much of power incident on this? So this I think, okay, we'll do one thing. Yeah. What is EI by delta T? Power incident on a surface. Some of you are getting confusion. I'll write it. This is the power incident on a surface. This I'll call surface here. If you want, you can give PI. So many symbols will get confused. Let's stick on to that one. So then what is EI? I can write it. I into pi r square into delta T. What is I? PS 4 pi no. So this incident energy on the surface open continuously will supply energy to the electron. When the energy of electron becomes equal to greater than work function, then it come out. let's see that for the energy of electron to become 4 electron volt, how much of time it will take. So therefore, what in place of EI I should write? The pi, that one, the work function of the metal. So this will be work function is equal to pi will get cancelled. R square 4x square delta T. What is delta T? Time taken by electron to come out of metal surface. This is what the classical mechanics or the wave nature of light is what telling us here. So if you calculate this, this will be delta T. If I solve it, I'll end up this one. We have to substitute all the values here. I'll check once. 56.8 seconds. It is what it's taking approximately. After what time the electron will come out of metal surface? Account of wave nature of light. This 40, 56.8 seconds. But let's do practically. I'll make the light incident on a metal surface. Then what I see that immediately what happened? The photoelectrons are ejected. So something went wrong, no? What is the wrong? The way I am trying to explain wave nature of light is wrong. So what we are assuming that the light will behave like a, when light is incident on a metal surface, the light will have the wave nature. The wave nature of light is what should be taken. That is the wrong thing. So shall we scold light? No. We should scold ourselves. The light will not behave like a light. The here, it will not behave like a wave. The light will behave like a particle. So there no, we should not scold light here. Here, what happened? The source, this will emit a light. It will emit energy. The energy will flow. It will get incident on the surface. But here, the light what happened when interacting with a matter, it will not behave like a wave. It will behave like a particle. That's what it's telling. But there's a time taken by electron to come out of metal surface. But practically, as we know, photoelectric effect is instantaneous. Instantaneous process, and it takes around 10 to power of minus 8 seconds is telling, or 18 I think. 10 to, some books given some different values. 10 to power of minus 18 is what you can take it, this one. So let me 10 to power of minus 8 or minus 9, anything it will be, or less. Photoelectric effect is instantaneous process, and it takes around 10 to power of minus 9 or less, 10 to power of minus seconds for photoelectron to be generated. So there's nothing wrong with our mathematics, everything. What was the wrong? The light will not behave like what we are thinking. It will not behave like a wave because I'm defining intensity. Are you getting the idea? I'm assuming that the wave nature of light, I'm trying to assume that one because the light is continuously incident on a surface. Then the electron will continuously absorb the energy. Once the energy of electron becomes greater than work function, it will come out. What I see is like something, but you see, instantaneous that one, 10 to power of minus 9 seconds. So there is a sum. There's the first problem what they faced here. Photoelectric effect is an instantaneous process, but according to wave nature, there's a time. So as you again decrease the wavelength, it may take 1 day. 56.8 seconds is something almost equal to 1 minute. As you further increase the wavelength, it may take 1 day. But we know it's everything is instant. If at all any electron should be ejected, it will be ejected instant or will not be ejected. So this is the first thing. Next again, I will increase the wavelength here only in the same experiment. I'm going to decrease the wavelength. Then as I keep on decrease the, as I keep on increase, I'm going to increase, as I keep on increase the wavelength. And what particular wavelength open, I don't see any photoelectric effect. Then the next thing is what they did experimentally. So I'm going for the next situation. This is the first part we did. Second one. So what I do is I'll get one threshold wavelength. I'll call lambda naught as threshold wavelength. If lambda less than or equal to lambda naught, there will be photo effect. There will be photoelectric effect. If lambda greater than lambda naught, there will be no photoelectric effect. What do you mean by this? So let me take again a source, this one. So the wavelength of this is lambda 1, I'll call it, which is less than lambda naught, threshold wavelength. Then I'll keep a surface here. Then what I see ejected electrons. Photoelectrons are being ejected. Getting this one? Because what is the thing? The light incident here, let me show systematically here, because this is the major idea of our discussion. Here what happened, we'll see. And there's an incident light.